My name is Jesse Haber-Kocharski, and I'm going to be talking about access control in Scylla in particular and security more broadly. I think I actually need my clicker. Should have grabbed that first. OK, so as the MC mentioned, I have a fairly diverse background in engineering and software development. And what makes me excited is to work on robust and simple software in highly technical domains, like self-driving. The thesis of this talk, the most important thing I want all of you to take away, is that the security of your data is important. And if it weren't, why would you be using a database in the first place? Importantly, most, or a lot, I should say, or increasingly, business value is tied directly to the data that you have. In some businesses, this is very readily apparent. In financial sectors, for example, information you have on past trades may inform how you bid in a certain auction. In a self-driving platform, information that you have on past pedestrian behavior may inform your model for how you navigate an intersection. And lots of other industries have these kinds of connections and indirect associations as well. And so when we talk about the security of our data, I want to shy away from maybe what you think of as security, like an alarm system on your house, and more broadly towards this idea that the data you have is important and you derive value from it, and you need to make sure that it has integrity, that your data is correct and untampered with, and you know where it came from and how it got to be the way it did. So I've established, I hope, that the security of the systems that you have is important. And so how do we think about these things? How do we talk about them? And one way that we can do that is we can define a common vocabulary for thinking about and describing properties of secure systems. And we're going to do this through security properties or principles as a way to frame our discussion. And there are lots of different collections of these properties and principles. There's one, I believe, called the CIA. There are others. The ones I'm going to talk about today are these 6. They're identity, availability, authentication, integrity, confidentiality, and non-repudiation. And what I hope to do is to describe Scylla's security features and discuss how they relate to these properties, so that we're going to use the same common language that security engineers use to describe systems in describing these security features of Scylla. And the first area I want to focus on is managing users and identity. So what is identity? Identity is, broadly speaking, the property that we want to know who is interfacing with our system. And in the case of Scylla, that means very simply who is interfacing with the database. And another important property is authentication. And again, broadly speaking in security, authentication is the concept that we want to verify the truth of some information that is provided by somebody who has been identified. And in the case of Scylla, what we want to know is, can we trust that this user who's presenting a certain identity to us is in fact who they say they are? How can we verify the truth of an identity? And in Scylla, these concepts are exemplified through users and passwords, as they are in many, many security systems that we use today. And so in Scylla, we can manage users directly through CQL. And in this example, I've created a Joe Smith user with a certain password, a very secure password. And I can identify myself to Scylla with this username. And we're all very familiar with that, at least if not in Scylla, more broadly with lots of other systems that we use. And in Scylla, the way we store this data is in a table in Scylla itself. We like to be recursive like that. So we have a nice table for users, and we store information. And when you log into Scylla, we query that table to identify whether or not you've been authenticated in the system. And I know this is likely review for most of you, but the way we actually manage passwords and store them securely is through what's called a one-way cryptographic hash function. And these are mathematical functions that have the property that, given a particular input, they produce an output, usually a stream of bytes. They have the property that pragmatically it's impossible to determine what the input was given a known output. So if I have a string dead beef in hex, it's pragmatically impossible within the bounds of computing that we have today to identify what password produced that sequence of bytes. And to implement password management on Scylla, we just use the cryptar function from the GNU C library. And this is a very historically stable function and series of functionality. And cryptar supports lots of different cryptographic hashing functions and schemes for doing that hashing. One of the most conventionally accepted and recommended schemes is called bcrypt. But unfortunately, bcrypt is often not supported on Linux distributions like Ubuntu and Fedora and others. So we fall back to SHA-512 most of the time. I think I wanted to talk about one more thing. Let me go backwards. Yes. Additionally, I want to emphasize that we add salt to our passwords. And for those of you who aren't familiar with that, the reason is that given only a cryptographic hash function and nothing else, an attacker could actually just collect a large database of common passwords and the resulting cryptographic hash because we advertise the function that we use, and they could just compare those directly instead of bothering to guess the actual password. So what we do is we add some extra randomly generated stuff to the password before we hash it, which renders these pre-computed outputs totally useless. And we do all this through cryptar as well. So I want to discuss also this concept of availability, which is actually a critically important security property that a lot of people don't necessarily consider, which is that our systems exist for a reason, and if we can't use them, they're effectively useless. And you're all probably familiar with denial of service attacks, or DDoS, distributed denial of service attacks. And what these do is they overload systems, rendering them unusable to serve regular requests from users. And again, if you have a building, for example, of secure doors and nobody can walk in your building, well, you can't do business. And you can imagine how this extends to lots of different things, maybe your own business. And so this idea that a system should be available to do the thing it's designed to do is a very important one. We address this in Scylla with users by replicating the user metadata. And we recommend that you replicate it based on n the number of nodes you have, which means that if a particular node is down, other users can still log into nodes in the system and access the database. You're not going to be locked out of the system. And lastly, I want to talk about identity management in enterprises. As I said, we manage all of this information in Scylla directly, but frequently in large companies, pardon me, they use external identity management or directory service tools, and this is very important, but boring on the surface stuff that allows you to manage all your employees' email addresses and contact information and groups they belong to and all this kind of stuff. And often they're very expansive, important systems. And we want to be able to integrate with these systems so that you don't have to recreate all that information in Scylla. And a very common way to interface with these kinds of systems is LDAP, Lightweight Directory Protocol. And we intend in a future version of the Enterprise Edition of Scylla to support this feature, and I'm actually actively working on integrating LDAP with C*star. So this is how we envision it working. Effectively, a client, whether it's a driver in code or somebody's typing at CQLSH, will provide an ID and password to Scylla. And Scylla will take that ID and from it, based on some user configurable rules, execute a query to your directory service, your DS. And the directory service will execute that query based on what Scylla passed to it, and hopefully it'll result in a single unique entry corresponding to one person. And given that entry, it's called a DN in LDAP. Scylla will then attempt to bind or authenticate the DN with the password that was provided. And if the directory service accepts it, then Scylla will acknowledge that the user has authenticated correctly. And one important thing to note about this scheme is, like systems which provide access via LDAP, this means that Scylla would be dependent on the availability of your directory service. And that could be an interesting constraint depending on your environment. But likely, you're not employing these kinds of systems unless you already have expertise at managing them. The second area I want to talk about, and I'm especially excited to talk about it because I refactored a lot of code and added support for a lot of this stuff, is roles and permissions and role management. And so an important concept in security is confidentiality, and I hope you're all familiar with this one. It basically says that we want the stuff that should be secret to remain secret. And we want to ensure that only the people who are allowed to access our stuff can. And in Scylla, this means that we want to limit who can read certain parts of the database. And another important concept in security is non-repudiation. And the definition of this is that nobody can refute the state of data, but that's a little hard to understand, I think. What it really means is that we understand exactly how data came to be the way it is. We understand who did what, when, what they did, and how they did it. And we can be sure of that information. So the combination of defining what exists in the database in terms of describing the different things that are in there, and how we decide and define who can do what is called authorization. Who's allowed to do what? And so we define a resource as basically an identifier for something in the database, and we have a resource describing a table, for example, or a key space encompassing many tables, or even a particular role, and I'll get to what a role is in a second. And we have a certain fixed set of permissions, like create or alter or select. And what we say is that a particular CQL operation is enabled or allowed given a particular combination of a resource and permission. So for example, if I say Joe Smith needs to be able to query the events table, then I can enable that functionality by granting the select permission to the events table to Joe, or to Joe Smith. And like with users internally, this is just a table in Scylla. And we have columns for a user, a resource, and a permission set. And so checking the permissions basically means that first, before executing any query, we have to query this permissions table for the combination of the resource and the permission and identify excuse me, let me go back a little bit. For the user and the resource, pardon me, identify which permissions have been granted for that user and that resource, and then make sure that the operation that's being executed is within that set of permissions. And so that means that every time we execute a query, we have to do the second query to check what the permissions are. And you might think that there's a lot of overhead doing that, and you'd probably be right. So we have a caching layer that caches all this stuff so you don't have to execute all these additional CQL queries. And that cache is a time-based cache. So after a certain amount of time, the cache will be evicted, and the data will be reloaded. And you can configure the time for that at the user level in the YAML file. And so this is a nice model. It works fairly well. But then you start to realize that there are difficulties in practice, and mostly operational. So if you have lots of different tables and lots of different types of data, and you have lots of users, then every time you add a new user, you're going to have to go through this hassle of adding permissions to the appropriate things for each one. And then the problem is even more annoying when you want to change permissions. You may have to repeat this change of permissions for many, many users. And this, even describing it to you now, it sounds incredibly tedious. And as we all know, when systems are hard to use and tedious, laziness usually wins. And so what people will frequently do in the face of systems that are hard to use is they'll try to subvert them. And how would you subvert a system like this? Well, you'd probably just have a user like developer with a password like Nintendo, and you give everybody the same username and password, and everybody just uses that. And the problem with that is that you're actually subverting and missing the point entirely of using users. All the benefits that we've talked about just go out the window, because now you have shared credentials, you don't have non-repudiation, you don't know who did what, you can't limit access to information. It's a big mess. So we want to avoid systems where doing the right thing is hard. We want to develop systems where doing the right thing is out of the hands of people. So a role is a concept that stems from this idea that if you have a large number of users, they're probably doing similar kinds of things. They're probably going to have access to the same kinds of data. And so what we do is we abstract this set of permissions and resources into a named entity called a role. So a role is just a collection of permissions and resources. And unlike users, we can assign a role to another role. So let me explain what that means with an example. Oop. Did I miss a slide? OK, I'm going to just go backwards after. So for example, all the analysts at our company are going to be assigned the role analyst. And all analysts need to be able to query the customers table. And Joe Smith is an analyst, so we're going to grant him the analyst role. And that means that Joe Smith inherits all the roles that have been granted, all the permissions that have been granted to the analyst role. And now let me go backwards. So you may be asking, well, what about users? And the interesting thing is that all users are roles. Roles are a generalization of users. I like to think that users are just roles that can log into the system. So there's a login flag when, if you allow a role to log in, I call it a user, but otherwise it's a role. And, but really, roles encompass users. Roles are the abstraction that we want to be thinking about here. So implementing roles it required lots of implementation changes to the code and refactoring and restructuring, but that's not really what I want to talk about. The most important thing is that logically, roles and their relationship to each other form a directed graph. And you can see in this example here that I have the Joe Smith user, the Tim Jones user, and I have two roles, analyst and team lead. And I'm going to grant analyst to J. Smith. J. Smith is an analyst, and Tim is a team lead. But also I want the team lead to have all the permissions of analyst. And so what that means is if we think about our graph that's formed, we see that an edge from one node to another implies that that node is a member of another node. So J. Smith is a member of analyst. So J. Smith is an analyst. And so if we want to identify the roles of all the roles of a particular user or of a particular role, we can just follow the graph. So T. Jones is a team lead and is an analyst. So we're just following until we can't go anymore. And so what we do is we implement this directed graph representation again in a table in SQL, in CQL. And we just do that as a collect an association from node to node with edges. And what's very nice about this feature of roles is that once we actually enforce the difference between a user, who is an individual, an identity, and a function, which is like what they're actually doing with the database, is now we get access to a whole lot of nice security features in addition to functionality features, which Avi alluded to, and I'll mention again in a second. So one of them is auditing. And auditing is a means by which we can record who's doing what at any time to the database. We can track who's issuing queries, which tables are affected, the IP address, the date, the time. And this is a feature that's available in the Enterprise edition of Scylla. And you can produce this information and output it into Scylla internal tables or syslog. And it's very configurable, and it's very fine-grained. And if you don't employ a proper separation between users and roles, you don't get to benefit from this information because you're going to be reflecting very broad information that's not particularly useful. So this is a very, very small example from our documentation. I think the formatting is a little bit off. I'm sorry about that. But you can see that T. Jones dropped the team roster from the NBA, and I hear they're really angry about that. So, before I go on, I did want to allude to what Avi mentioned earlier in his keynote, this notion of roles as being the way that we interact with the database rather than being tied to a particular user, because a user can inherit a role, means that when we talk about features like role-based SLAs or different kinds of workflows based on particular needs, we can actually use roles to talk about this and implement this internally. So if we, for example, have an analytics workflow and a real-time workflow, then maybe we can define an analytic role and do all our analytics workflows with queries with that role. And then we can ascribe or define certain performance characteristics of that role, of queries executed by that role. And having this model allows us to manage things like different access patterns in the database in ways that we really couldn't do before when we had this broad notion of users. Because how do you deal with an analytics user? You can only have one user at a time in the database for in a given session. So this is very useful and important stuff that actually has performance implications as well. And then very briefly at the end, I just want to talk about encryption, because encryption is something that I think we're all familiar with and comfortable with, at least conceptually. So integrity is one of the last properties, and integrity says, how do we ensure that the data we have is correct, is untampered with? And in the context of a database like Scylla, we want to ask, how do we know our data is secure when it's not being managed in a node's memory or whatever it is? How do we know it's secure in general, in a broad sense? And so we have one concept is called encryption during motion, and the thing that's in motion here is our data. And the idea is that as our data is being transmitted from node to node or from process to process, it's still secure, it's still encrypted. It can't be read, it can't be tampered with. And so Scylla supports encryption for data in motion in this way, both between nodes, when nodes are communicating, and also from clients to nodes. And we do that through TLS, which is a protocol used widely on the internet. It employs public key cryptography. And we use OpenSSL's implementation of TLS to do that. And then what's data doing when it's not in motion? It's at rest. And so encryption at rest refers to the idea that when the data is not managed by the database, the data is not being actively transported, we want it to be secure. And data in that state is on hard disks, usually, sitting in a server rack somewhere. And so in a future edition of Scylla Enterprise, we're going to support encryption at rest. And we're going to do that by encrypting at the application level the SS table files themselves at the block level. So we're going to split up each SS table file as it's being written, into blocks of 4,096 bytes. And we're going to encrypt each one with a user-provided key, a password. And so by providing this key, you can encrypt and decrypt the data at will. So how I want to conclude is I want to reemphasize that when we talk about security, we're not talking about police and alarms. We're talking about your data and its integrity and its safety and its validity. And that's important because increasingly businesses depend exclusively on their data to generate value and to make decisions. And if you can't be sure of the integrity and security of your data, there's very little else you can do. And so when we talk about secure systems, it's important that we use a regular and commonly agreed on set of words and concepts so that we're all speaking the same language. And this is the way that these features in Scylla help you to integrate Scylla securely into your own businesses and ensure that the data you're actually writing and reading from Scylla very, very quickly is correct.